Today we're going to continue with our description and exploration of data by looking at measures of variation. So there are three really important measures of variation that we're going to talk about today. The first is range, the second is standard deviation, and the third is variance. Variation talks about how spread out data is. And it's a very important topic. Just like with measures of center, we want to be able to not only calculate these things, but also know what they mean about our data. As with measures of center also, we have a round-off rule. And again, we're going to go one more decimal place than is present in our original data set when we're rounding for our measures of variation. When we're trying to find the range, what we're doing is taking the largest value in our data set and the smallest value in our data set, and we're subtracting. So we're finding out how far apart the largest and smallest values are. This is very simple to calculate. However, the range is not resistant to extreme values since it's dealing only with the maximum and minimum values. And since it's only dealing with the maximum and minimum values, it's also not taking into consideration where all the rest of the data in between the maximum and minimum fall. So let's take a look at an example of finding the range. So if we have Verizon data speeds of 38.5, 55.6, 22.4, 14.1, and 23.1, if we want to find the range, we need to identify the maximum value and the minimum value from our data set. The maximum value is 55.6, the minimum value is 14.1, and we're going to subtract maximum value minus minimum value, and we're going to find a range of 41.50 megabytes per second. Notice that there are two decimal places, even though the second one is a 0, because we have one decimal place present with our data. Another option we have is to find the standard deviation of a set of data. Finding the standard deviation is finding the measure of how much the data values deviate away from the mean. So we can find a standard deviation for a sample, in which case we use a lowercase s as our notation, or for the entire population, in which case we use a lowercase sigma as our notation. To find the standard deviation, we have a formula. To find it for a sample, we're going to take the square root of the sum of all of the differences, the data value minus the sample mean, squared, all of those differences squared, added up, divided by n minus 1. Now remember, lowercase n is the number of data points in our sample. So we'll take a look at an example of using this that'll hopefully clear up what's probably questions in your mind right now. Additionally, there's a second formula that when we look at it, it's a little bit more complicated. However, it's usually easier to use when we're using calculators and software. So for this one, you take n, the number of elements in your sample, you multiply it times the sum of all of our data values in our sample squared. So we're going to take all of our data values, square them, then add them up, then multiply them times the number of elements in the sample, or data points in the sample, and subtract from that the sum of all of the data points. So we'll add up all of the data points, and then we'll square that. We're going to subtract it from our previous product sum thing that we created, and we're going to divide it by the product of the number of data points in the sample times the number of elements in our data set, our sample, minus 1. So some important properties of standard deviation before we look at an example of calculating it. Standard deviation is a measure of how much the data values deviate away from the mean. It's never going to be negative. Because we're squaring everything, it's not going to be negative. And it's only 0 if all of the data values are exactly the same, so they all equal the mean, and so when we do all of that subtraction, we get a whole bunch of zeros to do the rest of everything with. Also, if we have larger values for our standard deviation, that means that our data is spread further apart, away from our mean. Also, if we have like an extreme low or an extreme high value in our data set, it's going to increase our standard deviation. Right? So our units of standard deviation, they're the same as the units of the original data. And when we look at sample standard deviations, so if we took a whole bunch of different samples from the same population, found the standard deviation for each of them, those standard deviations, those sample standard deviations, are not going to be centered around the population standard deviation. And because of that, we say that the sample standard deviation is a biased estimator of the population standard deviation. So let's take a look at an example of calculating this. Again, we're using these 5 data speeds. So we have our 38.5, 55.6, 22.4, 14.1, and 23.1 data speeds. To calculate the standard deviation, we need to first find the mean. We have done that previously. The mean of this data set is 30.7. And then what we'll do is we will take each of our data points and we'll subtract the mean from it. So we'll take 38.5 minus 30.7, and then we'll take that difference and we'll square it. And then we'll do the same thing with 55.6. So 55.6 minus 30.7, and then we'll square that difference. And once we've done that for all 5 data values, we will add them all up. And when we do that, we get 1083.0520. So in doing that, what we've done is we've come up with the numerator of our fraction that goes into our square root to find the standard deviation. Now the denominator is n minus 1. Remember, n is the number of data points that we have. So 5 is n. So n minus 1 is going to be 4 for us. So our standard deviation then will be the square root of 1083.0520 divided by 4, which is the same as the square root of 270.7630. And when we take that square root and we round to 2 decimal places, since our data has 1 decimal place in it, we find a standard deviation of 16.45 megabytes per second. Now that was the original formula. Now let's take a look at how this works with the shortcut formula. So for the shortcut formula, everywhere we have n, we're going to plug in 5 because we have 5 data points. And then we need to take each of our data values. In this case, we have 38.5, 55.6, 22.4, 14.1, and 23.1. We're going to square each of those and then add them all up, which will give us a sum of 5,807.79. And we're going to subtract from that the sum of all of our data values. So we're going to add up all of our data values and square that. So the sum of all of our data values is 153.7, and we'll need to square that. So following order of operations, we'll square 153.7, and we'll multiply 5 times 5,807.79. And once we've done those two things, then we will subtract the result, and we'll end up with a numerator of 5,415.26. In our denominator, we have 5 times the difference, 5 minus 1, which will be 5 times 4, or 20. So once we take the square root of 5,415.26 divided by 20, then we're going to end up with our standard deviation of 16.45 megabytes per second. Notice that they're the same, and in the second one, I didn't have to calculate the mean before being able to find the standard deviation. So, one important rule is that the vast majority, even 95% of our sample values lie within 2 standard deviations of our mean. And it's a rule of thumb, and it's really pretty crude, but it works out for us. So if a value is lower than the mean minus 2 standard deviations, or if it's higher than the mean plus 2 standard deviations, then we can consider it to be significantly different than the mean. And if it's within or between the mean minus 2 standard deviations and the mean plus 2 standard deviations, then it's not significantly different than the mean. So if we want to roughly estimate the standard deviation of a collection of sample data, we can use this idea that the standard deviation is going to be about the same as the range divided by 4. Now, this is a rough estimate. However, finding the range and dividing by 4 is significantly easier than using our standard deviation formula. So if all we need is a rough estimate and we need it quickly, this rule of thumb is a very good thing to fall back on. Now, for the standard deviation of a population, it looks more or less the same, our formula, except we're replacing all of our English alphabet letters with Greek alphabet letters. So we'll have lowercase sigma equals the square root of our sum of our data values minus the mean, mu, squaring that, and dividing by the population size. Now, this is the big difference, is what we're dividing by. In the sample, we divide by n minus 1, and for the population, we divide by the population size without subtracting 1. Now, another measure of variation that we can use is called the variance. The variance of a set of values is the measure of variation equal to the square of the standard deviation. So they're very related. Calculating them looks almost the same, except calculating the variance, instead of taking the square root, we just leave it as whatever would be under the square root. So the way we notate the sample variance is simply lowercase s squared. That is just the square of the standard deviation, and the notation looks like that. And the same thing for the population variance. Since the population standard deviation is a lowercase sigma, the population variance is a lowercase sigma squared. So just to review that, lowercase s's for samples, lowercase sigmas for population, and squared is variance, not squared is standard deviation. So the variance, things that you need to know. The units, when we have variance, are the squares of the units of the original data values. Since the standard deviation was the original unit values and the variance is the square of the standard deviation, that's likely not surprising. Also, the values of the variance can increase dramatically if we have really extreme high or low values, just like the standard deviation can. So again, it's not resistant, just like the standard deviation is not resistant. Also, the value of the variance is never negative, the same as the standard deviation is never negative. And it's the same reason we're going to square everything along the way. And just like the standard deviation, it's only 0 if all of the values are the same. The thing that's different about the standard deviation and the variance is that the sample variance is actually an unbiased estimator of the population variance. whereas our sample standard deviation was a biased estimator of our sample or of our population standard deviation. So why do we divide by n minus 1 when we're dealing with samples and not when we're dealing with the population? So when we look at the sample, if I were to tell you the mean and then tell you 4 of the data values out of a sample of 5 that formed that mean, you would be able to put together an equation and solve for that 5th data value. So that means that only 4 of the data values get to be chosen since we have that sample mean that we're working with. So we divide by n minus 1 because that last value is just automatically known since we know our sample mean. In doing this, because of all of that, what we end up with is a value that is closer to what our population variance value is instead of underestimating it or overestimating it. If we divided by n instead, we'd be underestimating our population variance fairly systematically. All right, so when we have bell-shaped distributions, remember this is that normal idea where it's symmetric and it's taller in the middle and shorter at the ends, then we have this empirical rule that tells us that about 68% of all of the data fall within 1 standard deviation of the mean, about 95% fall within 2 standard deviations of the mean, and about 99.7% fall within 3 standard deviations of the mean. So visually, this is what that looks like. We have our mean shown there as x bar, and we have 1, 2, and 3 standard deviations marked out. And you'll notice within the bell-shaped distribution, you'll see like 33 or 34.13%. That's roughly half of the 68%, and that's a little bit more exactly actually what the percentages are. And 68 is the rough estimate if we added those two 34.13s together. And same with the 95 and the 99.7%. So here's an example of how we might use that. IQ scores have a bell-shaped distribution. They have a mean of 100, standard deviation of 15, and we might want to know what percentage of IQ scores are between 70 and 130. Well, the empirical rule, we look at it and we say 70 and 130, they're each 30 away from 100. Well, that's 2 copies of our standard deviation of 15. So they're 2 standard deviations away. And we know that 95% of data fall within 2 standard deviations of the mean. So about 95% of all IQ scores are going to be between 70 and 130. So if the distribution isn't bell-shaped, we can use something called Chevys Theorem. So this says that the proportion of any set of data lying within k standard deviations of the mean is at least 1 minus 1 over k squared, where k is any positive integer number or any positive number greater than 1. All right, so if k is 2, then we're looking at the proportion of the set of data that lie within 2 standard deviations of the mean, and we'd have 1 minus 1 over 2 squared, or 1 minus 1/4, which is 3/4, or 75%. So we know that at least 75% of all values lie within 2 standard deviations of the mean. You might remember with our bell-shaped one, that was 95%, so the bell-shaped one is a stronger thing, but it's only applicable to those bell-shaped data distributions. This one applies to all data distributions. All right. So even though this is a smaller percentage, it applies more broadly. Okay, so unless you know the distribution's bell-shaped, this is the way you want to go. If you know it's bell-shaped, then you can use that standard rule before. So for 3 standard deviations, this is within 3 standard deviations, we do 1 over 3 squared, 1 over 1/9, 8/9, or about 89%. All lie within 3 standard deviations, right? And we could keep on going up to 4, 5, 6, and so on. So let's see what Chevys theorem says about IQs. Right. So applying Chevys theorem, we know that within 2 standard deviations, so between 70 and 130, 75% of IQ scores lie there. And between 55 and 145, 89% of IQ scores fall within that range. So sometimes we want to be able to compare variation in different samples or populations. We can use something called a coefficient of variation to do that. So if we have some non-negative sample or population data, we express it as a percent, where what we're doing is we're taking the standard deviation divided by the mean and multiplying it by 100%, and that gives us our coefficient of variation. So we can do that for a sample or for a population. So for a sample, we use sample standard deviation and sample mean, and for a population, we use population standard deviation and population mean. When we're calculating the coefficient of variation, we round it to 1 decimal place as a general rule. So really quick, sample standard deviation, again, is a biased estimator of the population standard deviation, which means that the values of the sample standard deviation do not tend to center around the population standard deviation. However, the sample variance is an unbiased estimator of the population variance, which means that the values of the sample variance tend to center around the value of the population variance instead of systematically over or underestimating it.